You are watching one of a series of videos giving an introduction to OrcaFlex. The first 4 of these videos, which we've called the fundamentals, are those that we would regard as prerequisites for looking at any of the other subsequent topics. If you are already familiar with these fundamentals, you may want to pick and choose the subsequent videos you watch based on your area of interest. If you're a complete beginner with OrcaFlex, I would strongly encourage you to watch the full series in order, as this will give you a good basic overview of the program, how to navigate it, and where to access and input data. It goes without saying that the quality of any OrcaFlex analysis is only as good as the quality of the input data, and that, of course, relies on the skill and experience of you, the user. These videos will help you to learn how to use OrcaFlex as one of your analysis tools, and I do hope that you find them educational and maybe even a little bit enjoyable too. We will look now at adding line attachments. Attachments are a means of adding objects or features to a line. These might be to represent such things as buoyancy cans or bend stiffeners, and they are attached to line nodes. The specific instances of an attachment are defined on the attachments page of the line data form, and the attachment types are defined on the attachment types data form. As soon as an attachment type is created, it becomes visible in the model browser. We will run through the various attachment types now, looking first at the clump type. The clump type adds mass and volume to the line node it is attached to. The combination of mass and volume will establish a submerged mass, which will determine whether the attachment is net buoyant, for modelling something like a buoyancy can, or net heavy, for modelling something like an umbilical termination head. We can see the submerged mass by looking at the properties of the attachment. As with other properties reports, this is done by using the context menu on the attachment types data form and selecting properties, or by using the shortcut Alt and Enter. If the submerged mass is positive, the attachment will be net heavy. If negative, the attachment will be net buoyant. The height of the clump determines how it is drawn in the 3D view, and if surface piercing will determine how much of the clump is below the water surface. The offset allows the clump to be positioned offset from the line axis, for example representing a buoyancy module which is connected to the line via chains or straps. Finally, we can choose whether to align a clump with the global axes, in which case the height will be represented by a vertical stick, half of the height above and half below the attachment point, with a positive offset being vertically up. Alternatively, the alignment can be to the line axes, in which case the clump will be aligned along the local z-axis of the line and no offset can be applied. Clump attachments can also include drag and added mass properties as defined on their respective pages. For examples of buoyancy modules using the clump attachment, we'll take a brief look now at one of our published examples, A01 Lazy Wave Riser, part of the example set A01 Catenary and Wave Systems, available on our website here. This example includes 2 methods of modelling buoyancy on a riser, distributed or smeared and discrete. The distributed type uses the line type wizard to create a line type with additional buoyancy based on float data input on this page. One of the benefits of the distributed method is that the line segmentation can be modified without influencing the position of the floats. Remember, attachments are attached to line nodes, so require a node to be present at the point where you wish to add the attachment. If the line you are modelling has continuous buoyancy, then using a line type would probably be better than discrete clump attachments. The discrete method uses attachments, as we have just been discussing. If we open the line data form for the discrete method, we see 20 attachments defined on the attachments page, and on the attachment types data form, we see the buoyancy module definition. The properties, accessed via the context menu, or the Alt-Enter shortcut, confirm that this module is net buoyant due to the negative submerged mass. We will come back to this method in a moment as we build a worked example. The drag chain type is used to simulate chains being hung from a line to increase drag and mass, as might be used in a controlled depth towing application. The flex joint type is used to change bend stiffness locally on the node it is attached to simulate a flex joint. Zero stiffness effectively makes a line pinned at that point. The bend stiffener type is intended for modelling bend stiffeners and can use a profiled homogeneous pipe line type to create a conical outer profile. We'll come back to this later and add a bend stiffener to the model we are about to build. We will now make a change to a riser model built in previous videos, where we learned about creating a data file in video 3, running a simulation in video 4, and the details of the line object in video 5. If you have worked through these videos, you should have the riser model already, but if not, I will recreate it now using the details in the table on the screen. Firstly, I will add a vessel and a line to this model. The vessel is positioned at the global origin and the default properties will be used. The line uses the default line type properties and its length is 200 meters. End A is connected to the vessel at a position of 35, 0 and -7 meters. And end B is anchored at a position of 190, 0 and with a height above seabed of 0 meters. The declination of end A is 175 degrees and the connection stiffness for end A is infinity. Finally, we have 4 sections in the line with lengths of 10, 70, 90 and 30 meters and segment lengths of 0.5, 2, 1 and 5 meters. Before adding the lazy wave profile to the riser, I would like to run dynamics and take a brief look at the performance of the model. So it has an oiler limit warning. The compression in the line isn't being modelled adequately. The properties report on the general object tells us it took around 13 seconds to run. And if we take a look at a time history result for the iteration count, it shows a number of spikes above 20. We can also see a chaotic line response at the touchdown region when we run a replay. We hope to greatly improve this line response by adding the lazy wave profile, as this should act to disconnect the vessel motion and the line touchdown. So let's introduce the lazy wave profile to the model by adding a number of buoyancy floats as attachments using the data in the table. On the line data form, we'll go to the attachment types data form at the bottom. To add buoyancy, the Clump attachment should be used. We can see on the data form that we can input a mass and volume, but the table only gives a mass and a submerged mass. We can enter the float mass and then use the properties report, the Alt and Enter shortcut, while modifying the volume until we reach the desired submerged mass. In this case we're told it's 0.75 tons buoyant, which means a target submerged mass of minus 0.75 tons. With a volume of 0.5 cubic meters, the submerged mass is only minus 0.0325 tons, so a larger volume is needed. 1 cubic metre gives minus 0.545 tons, so we're getting closer. In fact, 1.2 cubic metres is the volume which gives us the required net buoyancy of minus 0.75. We'll come back to the height in a moment, but we are modelling a buoyancy flow which we can assume will be wrapped around the riser. For this reason, we should set the alignment option to be the line axes. Having now created the attachment type, we need to place the required number of instances of that attachment type into the model. On the attachments page, let's add the first attachment, which is at an arc length of 90 metres from end A. Note the change in the profile of the line as soon as that attachment is positioned. If we take a look at the general data form on the reset page, the reset state, when using the analytic catenary representation, as we have here by default, includes buoyancy effects for lines. And this is why the profile of the line is changing in the reset state. Okay, we could continue to add all 8 floats one by one on this form, but here is another example of improving the efficiency of data input by using Excel. I'll add the first arc length of 90 metres into an Excel sheet, and I know that the next arc length will be 95 metres due to the 5 metre pitch spacing. Then I can highlight these two values and drag them down to create the required list of 8 items with 5 metre spacing. I can then copy this data and go back to OrcaFlex and paste it in. When I paste it, the program recognises the need for additional rows, and when we accept that suggested increase, we see our new data appear. I can also see that the lazy wave profile is now shown in the analytic catenary reset state. Remember that attachments are positioned on line nodes, so you should make sure your line segmentation is suitable for the desired clump positions. Clump attachments are often best visualized in the shaded graphics mode, so I'll go into that mode now using Ctrl-G. This shows me that the attachments might be drawn better with a different height. I'll go to the Clump types data form via the model browser and reduce the height to say 2 meters. So that gives me a better visual representation of these floats. When we rerun Dynamics again, first of all we can see it was significantly quicker. The General Properties report tells us the simulation took just over 2 seconds. It was around 13 seconds previously. And if we take another look at the iteration count as a result, we can see that the maximum iteration count is down to 3 now. And when we run the replay, we can see that the line touchdown looks much more acceptable. So with this lazy wave profile, we have successfully disconnected the vessel motion from the touchdown response. We will now add another attachment in the form of a bend stiffener. This is required to improve the riser response in the hang-off region. In order to look closely at the line hang-off, we need to zoom in on it. However, with such a large vessel heave motion, it keeps leaving the screen in the replay. We can make use of a View Parameters feature to lock the view to the vessel. Clicking on the Edit View Parameters button, or using the shortcut Ctrl-W, we can change the Relative To option from Global to Vessel 1. This results in the view staying locked to the vessel and allowing us to assess the riser response at the hang-off. You will see when zoomed out that with this view setting, everything now moves relative to the vessel, including the environment. Before we go any further, I want to point you to another published example, A01 Steep Wave Riser, part of the A01 Catenary and Wave Systems example set on our website. This example shows you a couple of ways of modelling bend stiffeners, the attachment method we are going to use, and a line contact method. With the line contact method, the bend stiffener is being modelled as a separate line, useful if you need to include the steel root section or model the rattle space or friction effects between the stiffener and the protected line. The accompanying PDF document to this file talks through the two methods in more detail. Another useful source of information is the page in the documentation about modelling bend restrictors within the line section of the documentation. Okay, back to creating a bend stiffener attachment. We obviously need to reset the model, then go to the attachment types data form. There are two routes to get there. As we already have a clump attachment type, we can open the data form from the model browser and then move to the stiffener page, or we can access it from the line data form. We will add a new stiffener type and optionally give it a name. Note that the next input required is a line type. The profile of the stiffener is created using a line type, which we haven't done yet. So we need to back out of this form and go to the line types data form instead. We'll add a new line type and give it a name. Because we want to create a conical outer diameter, we need to use the homogeneous pipe category. This also assumes the stiffener is made of a single homogeneous material. The data we've been given is on the screen. Firstly, we'll create our conical outer diameter. Remember from a previous video about line types, a variable outer diameter is created by clicking on the small down arrow to the right of the input box and selecting Variable Data. We now create a new data source and enter our data into the table. The stiffener will be 10 meters long, so the default arc lengths are okay. We just need to enter the diameters, 0.7 meters and 0.4 meters. We can look at the profile and optionally reverse it if we find we've input the data the wrong way round. Having created the new variable data, we select it as the outer diameter, then input the inner diameter and the material density. Then on the structure page, we need to modify the Young's modulus and Poisson ratio to reflect the material. Finally, we'll change the colour so that the stiffener is more easily visible. Having created the line type, we can now go back into the attachment types data form, and on the stiffener page, select the new line type. Note that when we do this, the length variable is greyed out, since the length is defined by the variable outer diameter. The final settings are for the connection point of the stiffener, which will correspond to the connection point of the attachment on the line data form, and the method of transfer of the axial load and inertia, which can be either at the connection point or over the full length. If the stiffener is effectively stuck to the protected line, such that the protected line carries the axial loads and inertia, then over full length would be the appropriate choice. If you wish to neglect the axial effects of friction between stiffener and line, choose at connection point. Now that the stiffener is defined, we need to add it to the line. So, on the attachments page of the line data form, we add an extra attachment, and then select the stiffener type we've just created. And then we need to position it at arc length 0 relative to end A. Having done this, we see it appear in the 3D view. You may find it's more obvious in the shaded graphics mode. Remember, if the conical profile has been set up the wrong way round, this can be reversed on the variable data page for the stiffener outer diameter. Note too that the variable diameter data, along with any variable data sets in OrcaFlex, can also be accessed directly via the variable data folder in the model browser. Okay, let's run Dynamics again and replay it with the view locked on the vessel. We can see that the line hang-off response is now much improved. Great news for this system design. One final point about stiffener attachments is that when you have included one in a line, you can access its derived properties by looking at the Line Properties report. Remember, this is accessible by using the context menu in the model browser. Having spent some time working with line attachments, our next video will look at the link object.